All right, so peptide synthesis. Well, how do we make a peptide bond? It says to form a peptide bond, the N terminus of one molecule has to be joined to the C terminus of another molecule. So you see that when we do this, not only do we form a peptide bond, but we end up losing which atoms? We lose a couple of hydrogens, and we also end up losing an oxygen. So I guess I should have circled it like this and like this. But anyhow, we end up losing water, right? We end up losing water and we make a peptide bond. And there are many different agents that can be used for making peptide bonds, but one of the most popular is called DCC, which stands for dicyclohexyl carbodiimide. Right, so this is the carbodiimide. I'm not going to quiz you on the functional group here, but DCC, again, very common reactant to be used to make peptide bonds. So we just take the peptides and we treat them with DCC, dicyclohexyl carbodiimide. Here is the mechanism of DCC coupling. Now, I am not going to ask you this mechanism. I never have on a quiz, never have on an exam, never seen it on a ACS exam. But if you take a look at just kind of the main points here, is that you start it with that carboxylic acid. Well, in order for that carboxylic acid to react with the amine as a nucleophile, it's got to be more activated, doesn't it? Because it is not going to be susceptible to a nucleophilic attack. And so we have a proton transfer, and then we have a nucleophilic attack where basically your carboxyl is attached to the DCC molecule, and what that does is it renders it more susceptible to nucleophilic attack by the amine. So this is your carboxyl end over here, okay, that reacts with the DCC. That's this molecule here. It's just a condensed version of it. And then it's activated right here. And then the amino portion, or the amine, comes in as a nucleophile. And we kind of do sort of a nucleophilic acyl substitution in a way. Of course, there's a proton transfer here. But anyhow, that's what happens. And we end up generating a peptide bond. Again, I'm not going to ask you the mechanism, but it is kind of cool to take a look at it. And the main points still stand. They're all things that we understand. Taking a poor leaving group, converting it into a good leaving group, and we have a nucleophilic attack and loss of that leaving group. Well, what would happen if I had some DCC and I just took any two amino acids with two different R groups? Here we have R1 and we have R2. If I combine those two amino acids with DCC, what am I going to get? Well, what I'm going to get is a mixture of 4 different dipeptides. Not very useful, is it? All right, I'm going to have R1 reacting with a molecule of R1. I'm going to have R2 reacting with a molecule of R2. And then I'm going to have each of the amino acids reacting to each other, but with each one's carboxyl and each one's amine to get these 2 different molecules over here. So again, not a very useful synthesis. So how do we, if we only wanted, let's say, this, for example, how would we do that, right? If we only wanted this one, how would we do that? Well, there's a way to generate only the dipeptide that we want. And let's see how we would do that. It involves protection, okay? What we would do is we would take the N terminus of one amino acid and the C terminus of the other, and we would protect both of them with a protecting group. Now you see, since we're protecting an amine and a carboxyl, we're probably going to use different protecting groups, but that's what we're going to talk about right now, is what are the types of protecting groups we could use. Because now that you've protected the nitrogen over here and you've protected the carboxyl group over here, the only thing that can happen is a reaction between this carboxyl, let me circle it, is this carboxyl and this amine, right? That's the only reaction that can happen. It's shown here. We would make that peptide bond, and then we could remove the protecting groups, and there you go. Now we have the dipeptide that we want. Well, again, what type of protecting groups do we use? Well, let's cover them. The first thing is that the amino group can be protected as a carbamate. So this is a new functional group, right? Everybody knows what an ester is by now. So an ester is when you have this, right? That's an ester. And when you have an amide, when you have an amide, that looks something like this. I'll just draw a secondary amide like that. Well, if you take one of those R groups, let's say on your amide, and you replace it with an oxygen like this, now you've got a carbamate. So that's what this is here, is a carbamate. So again, you protect that nitrogen as a carbamate, and let me show you what type of carbamate you use. So you use this molecule, which is diterbutyl dicarbonate. We call it Bach anhydride is what I call it most of the time. So we call this molecule here, we call this Bach anhydride. Bach anhydride, right? You remember an anhydride, like acetic anhydride, was AC2O. Well, here you have Bach 2O, and the Bach represents this part. So Bach, what am I deleting here that I didn't mean to delete? So the Bach part is all of this right here. So it's going to be all of this part here. That's a Bach. So you have a Bach there. You have a Bach here, which again is that terbutyl carbonate, right? You have two of them, and then you have the oxygen in the middle. So I call it Bach anhydride, and that's what most organic chemists call it. But anyhow, we end up putting the Bach group, which is in the orange box over here, to make our carbamate, and that is a good way to protect an amine. So we simply take the amine and we treat it with Bach 2O, okay? So Bach anhydride. All right, well, here's the mechanism for the Bach protecting group being attached to our nitrogen. First, we have a nucleophilic attack, which is kind of like a nucleophilic acyl substitution, okay, because we end up losing all of this part of the molecule over here. It's just pretty interesting, and that it ends up degrading, but that's neither here nor there. Then we have a proton transfer, and then we end up with our Bach on our nitrogen. So this is our Bach group on our nitrogen like this. A great thing about Bach is that it's so easy to deprotect Bachs, and we're going to talk about that in a second. But I just want to remind you that this molecule here, this is Bach 2O, okay, which is Bach anhydride. Sometimes if you're the kind of person that likes to Google everything that we learn in class, so sometimes it's just called Bach 2O like this, which is fine. And then other times it's called T-Bach, okay, 2O like this, because it is a tert-butyl. Anyhow, so there you go. If you want to remove the Bach group, what you use is trifluoroacetic acid. And trifluoroacetic acid uses the acronym, which is TFA, trifluoroacetic acid, right? If you have this, okay, this is acetic acid. So if we replace the 3 hydrogens with 3 fluoros, CF3, right, like this, this is TFA, trifluoroacetic acid. So it's a much stronger acid than acetic acid based off of what? You got your atom, no. Resonance, no. Induction, yes. Right? It's based off of induction, all those electron withdrawing fluorines that make this a really strong acid. So TFA, and you can remove the Bach very easily. Here's the mechanism for Bach deprotection. Again, it's kind of one of those mechanisms that I'll never ask, but I just want to take a quick peek at it because there's something really cool here. You do a proton transfer at the very beginning. Then you have this rearrangement where you end up losing a tert-butyl carbocation. You have a couple of proton transfers here. And then you end up doing another proton transfer. But and again, I don't expect you to be able to produce this. But the bottom line is that we end up producing what? Carbon dioxide when we do the deprotection, right? We end up losing this carbon and these 2 oxygens as CO2. And that is a gas that's going to leave the reaction mixture. So based off of Le Chatelier's principle, the production of carbon dioxide is what's going to drive the reaction forward. So that's why Bach deprotection is such a great reaction. Now, if you're wondering, hey, Mr. Dion, are there other ways to protect an amine, right, the nitrogen besides a Bach group? The answer is yes. There's a whole bunch of ways. But another way that's really popular is to use this molecule here, which is 9-fluorenyl methylchloroformate. It's a mouthful, but we just call that F-MOC chloride. So we call it F-MOC chloride, and that puts on an F-MOC protecting group. Okay, so you react the amine with F-MOC chloride again, which is 9-fluorenyl methylchloroformate, and you install that F-MOC protecting group. You can see that it's really big, isn't it? Okay, and it's also has aromatic rings in it, which renders it UV active, so you can view it by TLC, which is pretty handy, right? Running TLCs is really cheap and fast. Anyhow, the mechanism for the installation of the Bach group, the F-MOC group, is similar to that for the Bach protecting group. but we can remove the FMOC group just by using piperidine. And piperidine, okay, is this molecule here. It's shown here. It's a 6-membered ring with a nitrogen in it. This is piperidine. And all you need is piperidine. And what it does is it removes this proton here, and you end up with this resonance stabilized anion, which is aromatic, and then that undergoes a decomposition to give you carbon dioxide again. So also a very high yielding deprotection, the FMOC deprotection. Very easy too, very easy. I mean, you could get a 5th grader to run this reaction. You just literally throw piperidine at it, and it's going to work really, really well. So you see that at the bottom it says, just like Bach deprotection, it's the evolution of carbon dioxide gas that's going to drive that reaction to completion, right? Whenever you have a gas being produced, Le Chatelier's principle is going to be in your favor. All right, now how do we protect the carboxyl group? We've covered the amine. We said, okay, we got 2 ways. We can either use Bach, okay, we can either use the Bach protecting group, or we can use the FMOC protecting group. Either one of those. But what about the carboxyl group? Well, of course we can protect it as an ester, right? You know how to do that. This is just the formation of an ester under acidic conditions. So we take our carboxyl and our alcohol and aqueous acid. So this is just esterification, you know, it's really all it is, nothing more than esterification. And what is this alcohol? Well, it could be methanol, is used oftentimes. If it's methanol, then you'd end up with what? You'd have the carbonyl, and then you'd have a methyl group. Or sometimes we like to use benzyl alcohol, which is this, okay? This is benzyl alcohol, which we abbreviate as BNOH, okay? And what that would give you is this, okay, which we abbreviate as OBN, okay? So BN stands for a phenyl with a methylene attached to it. It means, so both of these structures in red mean the exact same thing, okay? And it says here that methyl and benzyl esters are the most popular, and we can use hydrolysis to break apart this ester, right? We talked about saponification, the basic hydrolysis of an ester, and that will totally work. But the thing is if you use the benzyl ester, right? This is the benzyl, right? This represents, okay? And I told you the shorthand is OBN for benzyl, okay? The reason the benzyl groups are so great is because you can deprotect them without using strong acid or strong base, okay? You can just use hydrogenolysis, which is just hydrogenation, just taking hydrogen and palladium, platinum, or nickel, and that'll just blow it off. So again, not strong acid, not strong base, just a party balloon filled with hydrogen. It's a reaction I've done many times. It works very, very well. Very good chemistry. Another option is to use hydrobromic acid and acetic acid mixed together. This isn't as popular. However, it will work definitely to remove that benzyl ester. So that's another reason why benzyl esters are just so popular. So if we take what we've learned and we put it all together and we wanted to make a dipeptide, right? Let's say we wanted to make, you know, this dipeptide where we have alanine and glycine linked together in this order, right? You see them down here. What would we do, right? Since we have the N terminus of alanine over here and we have the C terminus on the glycine, and this is just me kind of adding them in there to help you understand what's going on. Well, you'd have to protect rather the nitrogen of the alanine. What would you do? You'd protect it as a Bach. So you use Bach anhydride. There you go. What would you do to the carboxyl end? You'd protect that as a methyl ester. Could use a benzyl ester. Here they used a methyl ester. Nothing wrong with that. Then you do the DCC coupling. That makes the amide bond to produce the dipeptide that's protected at both ends. You use TFA, which is trifluoroacetic acid, to remove the Bach. Then this is just a saponification. Saponification to remove or hydrolyze the methyl ester. And there you go. That gives you your dipeptide, just like that. So, and if you're like, oh man, there's a lot of protection and deprotection, yeah, there kind of is in peptide chemistry. There is, because if you think about it, every amino acid's got at least 2 functional groups in it. So yeah, it does involve a lot of protection and deprotection. But here's something I want to tell you. I want to encourage you, if you ever think about doing research, is that these reactions, all these protections and deprotections, they're so commonplace that the chemistry has been worked out very, very well. And so again, the reactions are usually pretty high yielding and they work pretty well. And there you go. That would be the way to make your alanyl glycine. And so if we were to draw the structure of this compound, what would it look like? Let's see. You got N, oops, where's my pen? You got N, C carbonyl, N, C carbonyl. So since you treat it in base at the end, that actually wouldn't be this, would it? You'd have the unprotonated form here. So you'd have the amine, and then of course you have your alanine like that, and then there's no chiral center here. And so that would be the molecule you'd end up with in the end, right? Again, you end up with the carboxylate because the last step you treat it with base, and you end up with just the neutral amine again because it's in base. You don't end up with a protonated amine in base. All right, well, check this out. It says that everything that you've just learned, all these FMOC and BOC protecting groups and benzyl esters and methyl esters and all this stuff, it's great. Okay, using DCC is wonderful. It's great chemistry. But if you want to make a really big peptide, I'm not talking like a octapeptide. I'm talking like 50, or 100 amino acids linked together. Okay. Well, it says here that for every single amino acid that you add, you got to do 3 reactions. You've got to do protection, coupling, and deprotection, right? So that's a lot of chemistry. So there's a superior method for doing this, and it reduces the number of steps significantly. It's called the Meritfield synthesis, and Meritfield won a Nobel Prize for this. And the way it works is that you take the peptide, the molecule that you're making, and you tether it. Tether is just a sassy word for saying attach it to an insoluble polymer, right? What's an insoluble polymer? Plastic, okay? So you essentially put it on something that is insoluble like plastic, and that way the purification is just filtering it, right? Because it's not going to dissolve in an organic solvent. And we call this SPPS, solid phase peptide synthesis. Let me show you how it works. Okay, so you start with the C terminus. So you actually work backwards, right? If you're doing, if you have an amino acid, let's say you've got residue 1, 2, 3, 4. Okay, 1, 2, 3, 4. I don't know what they are. But again, this is your C terminus. Okay, and then this is your N terminus over there. Well, you would actually start with the C terminus. So you actually build it going from right to left. Okay, so you build from right to left. Again, the arrow, the way I have it written, makes it look screwy. So let me just change that. Right to left, like that. Okay, so here's what you do. This is your polymer. Okay, it's all linked together. It's a giant molecule that's totally insoluble in an organic solvent. But you see how you've got these little benzyl chloride kind of residues over here sticking off the end? Well, those are sweet, 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 tasty electrophiles just waiting to react with the nucleophile. So if it sees the carboxylate, it's just going to do an SN2 like that. And then you're going to have your amino acid, and you've got the C terminus. That's the carbon right there. You've got it attached to the polymer. So now it's stuck on there, and it can just be filtered off to purify it, right? Okay. So now you have the N terminus exposed, and it's got a BOC on it. And you see there's another one here, okay? Well, I mean, it's probably Avogadro's number, right? So what do? Okay. It says the C terminus is deprotected, and then you do the next coupling. So look, what you would do in the next step, it doesn't have it written here. I don't know why, but you would take it and you would treat it with TFA. That would remove both of the BOC groups, right? So then you'd end up with this molecule right here where you have the free amine sticking off the end. Then you'd react it with the next BOC protected carboxylic acid and DCC, and you make a beautiful new peptide bond. Okay. You've got your BOC group. What would you do? Treat it with TFA. Then go grab another BOC protected amino acid, and you keep on going and going and going and going until you're done. And then once you're done the whole synthesis, you would break this bond here. You basically rip it off of the polymer by treating it with hydrofluoric acid, right? It's one of those few times where I will allow you to use hydrofluoric acid, which is really dangerous acid, okay? So that's how it works. So The advantage to solid phase synthesis, you're like, what's so great about it? Again, since the molecule is attached on this giant polymer, right, this part is insoluble, okay? You don't have to purify it by chromatography. You don't have to do anything like that. You just filter it off. Trust me, filtering is a lot easier. So you just collect it by filtration, plop everything into the next reaction, and keep moving on and on. And when it says beads, it doesn't mean the beads on a necklace, okay? But the little pieces of the polymer are little spheres, okay? So they look like little beads anyhow. And now this whole process is automated. We actually have peptide sequencers who can just, build the peptide reaction after reaction. So Meritfield won a Nobel Prize for this. And anyhow, it's pretty cool chemistry when you think about it. All right, so this question says, identify all the steps that you would need to make this tetrapeptide using a Meritfield synthesis. So let's see how you would start. So again, this one over here, this is our C terminus. So that's where we're going to start, is with this phenylalanine. And then, son of a gun, this is our N terminus over here. So we're going to end with that one. All right. So let's start with our phenylalanine. The first one, I know it's on there twice. So I'm going to draw the structure of it like this. Yeah, anyhow, like this. So we have an N, the Bach protecting group. So you still have one of the hydrogens, so it's NH Bach. Then you have the carboxylate salt like this. And what we're going to do is we're going to react it with the polymer. I'm going to call this the polymer. I'll just shade it in like this. Okay. So again, right, you take a N-Bach protected amino acid. So you see you have NH Bach. Okay. Here they haven't written it as the carboxylate. I just decided to, because you could, buffer it so that it exists as the carboxylate, right? And then that would just do what? That would do the SN2 reaction. Okay. So what are you going to end up with? You're going to end up with this. Oops, where's my black pen? Write it like this. Here's your polymer. Here's your methylene. Then you've got phenylalanine. Okay. And then attached to that, why don't we just write Bach like this? Okay. So the next step is going to be to remove that Bach. So you treat it with TFA. And now you've got the polymer, ethylene, your phenylalanine. Okay. And I mean, you could write the NH2 if you want, if that helps you understand what the heck is going on, but I think it's okay the way it is. So next we're going to attach the next residue, which is the valine, right? So next we're going to react this with DCC, and we're going to react it with valine, okay? That's got a Bach group attached to it, right? There we go. So then what are we going to have? We're going to have the polymer, methylene, we've got the phenyl, and then we're going to have a valine attached to it, and then it still has the Bach group on it, of course. And then we're going to remove that Bach group using TFA. So we'll treat this with TFA. Then we end up with the polymer, and then we have phenylalanine, and then we have our valine. So then what are we going to do? We're going to attach the leucine to it. So let me just, we'll do the leucine in red. Okay, so next we're going to attach the leucine. So we're going to take this, and there we go. So we're going to treat it with leucine with a Bach group on it, like that, with DCC. And that's going to make this, where we have the polymer, our phenylalanine, we have our valine, then we have our leucine, which has its Bach group on it. I'm going to deprotect that using TFA. See if I can use a little copy paste magic here. Paste this over here. So I'll use my eraser. And this is where we are. Okay, so I'm going to go to the next slide because I planned appropriately, knowing that this takes a lot of space. So copy this back over here. So paste it in here. And now I'm going to react with the last phenylalanine. So I'll take it and I'll treat it with phenylalanine with another Bach group on it and DCC. Then I end up with the polymer. You know what? Maybe I should just use the old paste thing again. There we go. And now I've got another phenylalanine over here. I've got the Bach group attached to it. All right. There we go. And what are the last two steps going to be? First, I'm going to treat it with TFA, right? And that will remove, that's going to remove the Bach group, okay? And then after that's done, I'm going to treat it with HF, okay? And that's going to remove it from the polymer. Move polymer, okay? And then I'm going to end up with this molecule, just like that. And there you go. Nothing to it. And that's the final answer. And that is the Meritfield synthesis, just like that. All right, last couple of sections, which we're going to skip, deal with protein structure. I recommend taking a look at this if you plan on taking biochemistry later. So this section deals with primary, secondary, tertiary, and quaternary structure. Primary structure is just the order of the amino acids, the order in which they come in the protein. Secondary, that involves an alpha helix and a beta pleated sheet, and there's some information about alpha helices and beta pleated sheets. Tertiary structure is when we have the three-dimensional structure of a protein, right? Because I told you it can have all these different conformations. And so it talks about the folding of a protein, and we talk about denaturation a little bit. And then quaternary structure, that's what results when we have more than one protein with tertiary structure and they conglomerate together or aggregate to form a new protein. Hemoglobin would be an example of that, or fetal hemoglobin would be another example. And then the very last section talks about the function of proteins, like fibrous proteins, like keratin and things like that. And it talks about how an enzyme is nothing more than a protein that just acts as a biological catalyst, which serves to speed up a reaction. Then it talks briefly about transport proteins like heme, which have these iron 2+ ions complexed inside the porphyrin ring, and that can carry oxygen around the body.